Laura Capelli is assistant professor at the Department of Chemistry, Materials and Chemical Engineering, Giulio Natta of the Politecnico di Milano, Italy. Her research activity is related to odor science and engineering, focusing especially on odor sampling, development of electronic nodes for environmental air quality monitoring, dispersion modeling, and characterization of odor emissions from different industrial activities. So please, Laura, can you enlighten us?
Thank you for this introduction. Okay. Good afternoon, everybody, and thank you for the introduction. There is nothing more I should say about myself. Besides that, today I'm talking about our latest findings at Politecnico di Milano in the field of area source sampling. We are a university, so what we usually do is mainly research. So I will talk about that today, and I will address the problem of what is the best way to assess odor emissions from area sources. Point sources will not be discussed here, as you all know, they are not problematic at all. It's maybe too simple, but they are quite easier to be sampled than area sources. Historically, area sources have been divided into active area sources, which which are typically also not too much of a problem because there is a sampling methodology that is widely accepted that foresees the use of static hoods that in some way make the active area source as a biofilter, for example, similar to a point source. For passive area sources, the question is more complicated, and it's still a quite debated task, especially also in the WG2 group for the revision of the EN 13725, and so it's something that still needs to be investigated. First of all, before getting into the subject, one important thing is that the problem is defined by identifying the different types of area sources that require to be considered in a different way. And so based on our most recent studies in this field, we identified at least 3 different kinds of, I prefer to call them non-active area sources, which have to be treated differently since they are characterized by different volatilization and emission phenomena. And we have this distinction into 3, which is liquid passive area sources, like wastewater treatment tanks, for example, most common example, solid passive area sources as contaminated soils, and then the third category, which is not the does not belong to the traditional distinction, are landfills, since in our opinion, landfills should not be considered properly as passive area sources, at least because the phenomena that characterize volatilization and emissions from this kind of source is quite different than it is in the case of solid passive area sources, as will be discussed, as I will explain further on in this presentation. As in general, the estimation rate values from passive area sources or from non-active area sources may be performed using either one of 2 different approaches. In literature, you can see some studies talking about indirect measurements using micrometeorological methods, where emission rates are derived from simultaneous measurements of wind velocities and concentrations across the plume profile downwind of the source. I say in literature because in fact this is not so much more applied in practice, and what the methods that are typically preferred are so-called direct measurements. Qua mi è sparita una parola, something, a word disappeared, see. which are usually preferred. These strategies use an enclosure or a hood of some sort, and in this case, what happens is that the hood is placed over the source to be monitored. Then a natural sweep airflow is sent inside the hood, and the sample is collected at its outlet. Then the emission rate is finally calculated by combining the information about the odor concentration of the sample collected at the outlet of the hood and the geometrical features and operating conditions of the hood itself. State of the art, for liquid passive area sources, sampling strategies typically involve specifically designed wind tunnels that isolate a portion of the surface to be monitored. This is an example of the wind tunnel we use at our lab and which is commonly used also in other labs in Italy. Wind tunnels can be operated at different neutral airflow rates, and that's already a degree of freedom which on which not everybody agrees. One possibility is to use higher airflows in the range of 10 centimeters per second or up to 1 meter per second, which has the advantage of simulating more typical wind conditions that may occur on the surface to be sampled. But the drawback of such high airflow rates is that they tend to dilute a lot the emission, and so to give other concentration values that are practically difficult to be measured. For this reason, we at least, but it's one possibility is to use low-speed wind tunnels, so wind tunnels that are operated with airflows that give velocities of 1 to 10 centimeters per second inside the hood. About solid passive area sources, the question is even more complicated because sampling strategies are not at all univocally defined. There are several situations in both wind tunnels or flux chambers are used by different labs. We at Politecnico tend to prefer wind tunnels since the fact that they have a directional flow, in our opinion, better simulates what happens in real conditions of wind action on the surface. However, to be true, there are no so widely accepted notions concerning sampling, nor the nature of the volatilization phenomena inside the chamber is fully understood. So there are a lot more of uncertainties concerning both the optimal features of the sampling device and its operating conditions. For landfills, what happens is that the question is even more problematic. Why should they not be considered as passive area sources? First, they have a minimal, yet not negligible emission flux from the surface in the range of liters per square meter per hour. But the main problem is that this emission is not directly affected by the wind speed over the surface itself, as it is the case for passive area sources. So, in this case, it is necessary that sampling strategies involve the use of specifically designed hood, and since landfill surfaces typically should be have low emissions in terms of odor, wind tunnels should generally be avoided since they tend to overestimate emissions drastically. For the measurement of landfill gas on landfill surfaces, there are two, let's say, main approaches, which the one that uses a static hood, which is the English method, and then there is the American method that provides to use flux chambers, so fluxed hoods. Which is best, I cannot answer. I can tell what we decided to do and I'll tell you later. So then, moving on, the problem of sampling on area sources is not only to get representative odor concentration value, But since in many cases odor dispersion modeling is the preferred approach for regulations in many countries, it is important that this odor concentration is in some way turned into an odor emission rate. And this is another very complicated issue. In the case of liquid passive area sources, as I showed before, there is an equation that can be used to get the specific odor emission rate, or in turn the odor emission rate from the odor concentration. And in the equation there is the term of the sweep airflow that is sent inside the hood. So once you calculate this specific odor emission rate, you should know that the value you obtained in this way is only representative of the specific sampling conditions of your hood. So in other words, this is the specific odor emission rates that is referred to the sweep airflow rate that was sent inside the hood during the sampling. So that is not necessarily representative of what happens in the open field when the hood is not there, of course. And that is the problem you have when you want to use dispersion modeling afterwards. So what can you do to recalculate your specific odor emission rate from the conditions inside the wind tunnel from the conditions outside the wind tunnel? There is a widely adopted method that for this recalculation that assumes that the specific odor emission rate and the odor emission rate are proportional to the square root of the sweep air velocity. This approach is based on the Prandtl boundary layer theory for laminar regime. And that is already an approximation that is not really fantastic, because in open field, laminar regime is not typically what happens. You typically have a turbulent flow. Then this equation also entails other approximation, like considering the effect of placing a hood over the surface totally negligible, and it's not true, of course. And also, in this form, it assumes flat wind profile, which is, of course, not true as well. So what did we do in our research activity to try to give to create another model for the estimation of odor emission rates from liquid passive area sources? First, it is our belief that it is very important in any of these sampling strategies to be able to describe accurately the volatilization phenomenon inside the wind tunnel. It is important to understand what happens inside your hood before you can relate it to anything else. So, and of course to relate it to the conditions in the open field. So our idea was to relate the models that describe the behavior inside the wind tunnel, which can be found from the Prandtl boundary layer theory and so on, to other semi-empirical models that can be found in literature that describe emissions from pools in the open field. There are some models, like the one proposed by Kawamura, that gives you what is the emission rate from an open pool in function of the wind velocity at 10 meters. And our idea was to combine these two models. The models that we choose are those two. For the open field, the one developed by Sutton that can be found in this book, and for the interior of the wind tunnel, the Prandtl boundary layer theory, and in particular we considered the model for the flat plate. We also considered the two parallel plates in our studies, because in fact the wind tunnel, of course, is not properly a flat plate, even though, as we will see, it's the model that better approximates the results. What we did afterwards is that, since our wind tunnel has a very particular geometry that doesn't fit to any of these two models, we passed to an experimental phase in which we tried to see which model applies better to our sampling system. We decided to work with acetone and butanone for a lot of good reasons, safety and the fact that we could detect it with our instruments in the lab, and that they are compatible with the wind tunnel materials and so on. And we got some interesting results, very reproducible. But as you can see, the red dots of the experimental results are clearly biased with respect to the models. The trend is more similar to the trend that is foreseen by the flat plate model, so we decided that this better approximates our results. But in both cases, we have this bias, and so we decided to correct the proportionality coefficient for the calculation of the mass transfer coefficient from the theoretical model into another model which better describes our experimental results. Since at the end what interests us is not to have a theoretical model, but to have the model that describes our sampling system. Then you can equal the two models and in some way obtain a correlation between the airspeed inside the wind tunnel and the wind speed at 10 meters. By doing that, oh mama, what happened here? Maybe I should have checked the presentation before making it. Vabbè, I'm sorry that there's something that didn't work. You get to this new model that, with respect to the old one, let's say, has an exponent of 0.78, which is the typical exponent of the turbulent regime and not of the laminar regime. And then you have this ratio that uses this new recalculated velocity that is obtained by the equaling of the two models. My God. Oof, vabbè. Anyway, this is the new model, and these are the results that we extrapolated for other different compounds. Since there is the diffusivity term inside the equation that we saw before, of course this model is compound specific. So for compounds having different diffusivity, you will have slightly different results. However, if you consider the compounds that are typically of interest for olfactometry, they do usually not have so much different diffusivities, and it turns out that the variability of this model is contained within a range of plus minus 10%, which is not dramatic. Of course, this is a new proposal. We have not published yet. We are writing the paper right now, but we believe it is already sort of improvement from the traditional old model. But of course, this will require further studies and, of course, validation, as any model does require. For the estimation from passive, of odor emissions from passive aerial sources, we are quite still far away from a solution of the problem, but because the model that describes the volatilization from solid, it's quite more complicated. You have to consider, of course, also the diffusion inside the solid itself, so its porosity and so on, the interaction of the diffusing compounds with the solid, and also the thickness of the layer that is interested by diffusion. So there are a lot of different parameters that make the whole thing more complicated. However, we try to schematize the problem this way, so having a layer of liquid with a solid over it. And in this, by doing that, and the gas phase here, so you have a double contribution of diffusion from the liquid to the solid and through the solid then to the gas. And in this way, we were able to write an expression for the outlet concentration in the gas phase. Then we passed to an experimental study as well. In this case, we didn't use the the normal wind tunnel we use in the field, but we decided to use a specifically adopted and designed lab-scale wind tunnel, which allowed to schematize the problem in the way I showed before. And also in this case, we decided to use acetone as a liquid compound. And to simulate the solid, we used glass microspheres. These are inert, and once you know their diameter, it's easy to get their porosity and so on. So it's a solid that is easy to characterize if you want to write a model. Oh my God. Okay. Also in this case, the model that seems to be more accurate in describing our experimental results is the flat plate model, again. And it's the one more capable to predict the experimental concentration trend. In this case, we don't have this bias as we had in the other case. The wind tunnel is, of course, different. This allowed us to write an updated expression for the outlet concentration. And what is interesting is that in this expression, you can see that if the diffusion into the solid is inhibiting, so if the diffusion coefficient inside the solid is very low, then you have a situation in which your outlet odor concentration is proportional to the sweep air velocity elevated to an exponent of -1, which on the other hand means that you are approaching a case in which your odor emission rate is constant with respect to the sweep air velocity. So it is not influenced by the air velocity, which is already a very interesting consideration. This is the case when the diffusion inside the solid is so slow that you have a sort of drying out of the solid surface. In the other case, when the solid is very porous or when its thickness is very low, you have a situation in which you approach the liquid case only. And so you again have a situation in which the outlet concentration is proportional to the air velocity elevated to an exponent of -0.5, so similar to the liquid case. And about solids, that's all for the moment. The researchers are still going on, of course, but I'm not able up to now to give more accurate models. Then, what about landfills? So we recently published a paper in which we compare different approaches for the estimation of odor emissions from landfill surfaces. And we tried a little bit of everything. First macro approach is the idea of direct evaluation of the odor concentration on the landfill surface. Here I'm talking about the exhausted landfill surface, so I'm not referring to the fresh waste and so on. We decided to concentrate on that as a first step. So first idea was, okay, let's try to use what we usually do on passive area sources, which is the wind tunnel. So we tried out that, and what turned out is that we were terribly overestimating emissions. So this approach was considered as not suitable for this specific case. So another possibility was to use flux chambers. Flux chambers are used by the US EPA in their guidelines, and they are typically flushed with lower fluxes, so maybe we thought the effect of overestimation might be more limited, and that's something we tried. Again, the problem is on the exhausted landfill surface, the odor emissions are not so high. So also when using flux chambers, the problem is that the interaction between the odor concentration that you measure at the outlet and the odor concentration of the soil itself might create some problems, and so you might still have a problem of overestimation. Then we tried something different. The idea was to assume that there is possibly a correlation between the emissions of landfill gas and the emission of odor from the exhausted landfill surface, and so try to estimate the landfill gas emissions. How did we do that? In one case, we tried to use the softwares that are typically used for the estimation of the landfill gas production. Then we subtracted the quantity of landfill gas that is burned, that is collected, and so we tried to estimate the landfill gas emission this way, and we realized that's not a good idea. because the differences you can have by changing the input parameters of the LandGEM models, or we also tried to modify it in a more intelligent way, at least we thought, but still, you can have so big differences that then by subtracting the quantity of collected landfill gas, which on the other hand is something you usually know from the management data of the landfill, you get emissions that are from 100% to -20. So really the variability was too much. So another idea was to measure the methane concentration of a landfill surface directly, either with static hood, English method, or with flux chamber, American method. So we did that. And in a first study, first we designed our own hood, because we wanted to have only one, which could be operated in both methods. And still, our static hood was not really a static hood, because our design was inspired by some studies we found in literature, especially one paper of a German group of 2013, so very recent, in which they decided to use a tube that connects the hood, the internal of the hood to the exterior, so that you don't have overpressures inside the hood, which might interact with the emissions from the soil. So this was the idea, and we designed this hood, and our preliminary results that we presented, I think, at the NOS 2 years ago, showed that if they are properly designed and correctly operated, in both cases you get similar estimation of the the specific flux of landfill gas. So once this was assessed, we chose to use the static hood method, because of course from a logistical point of view this is much easier, because you don't have always to provide the air supply, which is quite complicated, especially in cases like landfills, where you have to do more sampling points that are often far away from each other, and having the tank to carry out all the time, carry with you all the time, it's not so practical anyway. So we did that, and we tried to estimate the emissions of landfill gas from a landfill surface, and we also tried to find a correlation between the landfill gas emission and the odor concentration. We found a moderate correlation. We found an average value of landfill gas emissions on the surface, which is equal to 0.39 liters per square meter per hour, which is very similar to other recently published research by other Italian groups. I say Italian groups because if we compare these emissions with landfills in China or in Korea, you might be very surprised that the orders of magnitude might be very different, but this may be due to the different operational condition and different quality of the waste that is landfilled. And then we estimated, thanks to this correlation, another concentration of the landfill gas, giving a specific odor emission rate of 0.011 odor units per square meter per second. This can be considered as an odor emission factor if we assume that the landfill surface can be considered as the activity index of the landfill. And this also was published this year in Atmospheric Environment, so if you want more information about that, you can find them there. And as a final remark, again, I want to highlight that we believe it's always very important to understand what happens inside your hood. Before you, probably this slide should have been described before the previous one, because before you accept the results that you get from your sampling system, you have to be sure that you have understood how your sampling system is working. So we did that, and in this case we decided to apply computational fluid dynamics, which is quite complicated. So this was a choice that we considered forced, because we had to at least verify the two hypotheses that underlie the sampling system as we used it. First, that the growth of the methane concentration inside the hood is linear, at least for the deposition time we used, which we fixed at 10 minutes, which was reasonable enough to read something with the FID that we used as the measurement instrument, and that was not too long, again, for logistical reasons. And also, you have to be sure that the concentration that you are measuring with your instrument is representative of the average concentration inside the hood. And that is not banal, because you are talking about a static hood where you have only diffusion from the soil of something that comes out very slowly. So it's not banal at all to say that what you are sucking from inside the hood is representative of the average concentration inside of it. But it turns out that the mixing that is caused by the FID causes an homogenization of the interior of the hood, even though we already thought of an improvement which could be adding a little mini fan inside the hood to make everything more, even more homogeneous. And that also we published it recently. This thing about publications is not for self-celebration, but it's to show you that it's all works of 2016. So it's really something that is extremely recent and on which we are actually currently working on all the time. And of course, if someone is interested in reading more about that. To the conclusion, I know I was long. The conclusions are easy. The sampling strategies or an area sources should be differentiated considering the different source types. So in our ideal liquids, solids, and landfill surfaces. And then again, the understanding and the descriptions by means of suitable models of the volatilization phenomena that take place inside the hoods and that constitute the odor emissions are fundamental for the evaluation of representative odor emission rates. Of course, this is all very complicated, and as far as our research work is concerned, this will require a lot of further experiments and validation and so on. But of course, there is not only research, there is also standardization, which is important. And in this moment, as I said in my introduction, there is a problem about in some way improving the first version of the EN 13725 by adding some more information about how to carry out the sampling on area sources. And of course, from what I presented today, I think it's obvious that we are still far away from getting to a unique solution of how, what method to use and what equations to use, what models to use. This will require a lot of other work. Still, something must be written, and what will be the approach in the revision of the DN? Probably, not only probably, that's presumably what will be done, is to propose a target approach, which means that no specific indications will be given about how the hood should look like, but indications will be given about how the hood should perform. So fixing a set of experimental conditions for an experimental setup with a given liquid, which is probably acetone, since the most data we were able to collect from the participants of the group concerned the use of acetone. So it's the compound for which we have more data available at the moment, and that's the only reason why considering it. So for a fixed experimental setup, the hood should perform in a certain way, of course, with a given uncertainty range. So this is probably the approach that will be adopted now in looking for further improvement, maybe for the next revision in I don't know how many years. I thank you for your attention, and if you have questions, I'm here.
there any question? I'm not gonna do all the questions here. Eh? Oh.
When you were considering the wind tunnel on porous surfaces, not on the liquid surface, but
Yes.
on a compost surface or whatever, did you consider where the air goes when you blow it into the wind tunnel?
Yes, in this case, it cannot go anywhere because it's closed. But of course, in open field applications, this is a point. I do not exclude that in some cases it could be probably possible to take a sample of soil and put it in a lab scale wind tunnel.
I don't mean that. I mean, when you have an airflow through a wind tunnel, it doesn't all come out of the exit.
In this case, yes.
It leaks.
It's
in
closed.
practice, it leaks around the edges.
In this case, no. It all come out. All comes out. It was totally closed and sealed. So what went in went out.
Just
and we measured it at the inlet and at the outlet to be sure that we didn't have leaks.
You just looked at the ideal situation.
Yes.
Not a practical situation.
No. That's what I said. We schematized it in a very simple way, and we didn't have a soil. In fact, we had a liquid, an emitting liquid on the bottom, and then a layer of porous solid above it. So it's far away from the real situation. It was just a way we adopted in order to be able to write some kind of a model describing it. But of course, it's still a step behind what should be done in the...
And the same sort of question about landfill emissions. Landfill emissions are not usually affected much by the wind airflow over the surface, but by changes in atmospheric pressure. So by changing in atmospheric pressure.
I didn't understand.
Well,
sorry, the question.
Meteorological conditions where the atmospheric pressure, you get a low pressure area, and then you get an emission from the landfill because the pressure in the landfill is higher. It's nothing to do with airflow over the surface.
No, in fact, the airflow on the surface has nothing to do. That's why we didn't flush any air in our measurement method. I didn't show it here, but we tried to we measured all the atmospheric parameters for all the year of measurements that we have run, because it's true that everybody's saying that when the air pressure is low, the landfills are emitting more, and that's reasonable. I mean, I wouldn't expect it to be different, but in fact, that is not published anywhere. There is nobody showing a real correlation, a quantification of this effect, or a real correlation of that. So we tried to do that. So we measured all the atmospheric parameters together with soil humidity. So we took a sample of the soil and measured humidity in our lab, pressure, temperature, wind speed, and whatever, all the atmospheric parameters we could measure. But unfortunately, things were not so clear. We recognized a clear correlation between the soil humidity and the emissions. But this is, in our opinion, more due to the specific characteristic of that landfill. And then also correlation with the pressure, with atmospheric pressure, but not with the instantaneous pressure, but with the gradient of the pressure of the previous 24 or 48 hours. But I have to admit, correlation were not so exceptional, and this probably also will require further investigation to be sure of what we are stating. It's not easy at all, especially because the measurements entail, as you all know, environmental measurements entail a high degree of uncertainty. So trying to make these correlations is sometimes a very hard task.
as I understand it, referring to the process of standardization, you reached some result on the level on the method on liquid surfaces.
Yes.
So
yes,
that one could
yes,
be standardized.
What I recently did, because that was what came out after the last meeting of the group in Delft. These are the data that I discussed with the convener of the group, with Ton, together with other data that I received from the German group and from another group, always on acetone. The difference is we work with pure acetone, they worked with diluted acetone, so the numbers are of course not directly comparable, but of course from the experimental conditions that you have, especially of airflow, temperature, because temperature is very important in this case because the volatility of acetone changes very much with already 2 degrees of temperature differences. And by measuring, of course you cannot directly compare the outlet concentrations, but what you can do is to evaluate the mass transfer coefficient that you have inside your hood. And what I noticed at the first look into this data is that the results that were obtained in these 3 different labs working with 3 different hoods give mass transfer coefficient, which is not of course the same, but at least which is in the same order of magnitude. So, since one point is that Germany has its own guideline on sampling, so you just can write something that excludes their wind tunnel from the possible wind tunnels to be used for sampling. The idea was not to say, okay, the wind tunnel must, not to have the German approach to say the wind tunnel must be built like that, long like that, and so on, but to say, okay, you are free to choose your sampling system. And in extreme situations also, flux chambers could not be excluded by such an approach. What you have to prove is that on a certain, when you put them on a solution of water and acetone ranging from a concentration from 0.2% to 100%. I don't know because the numbers are not fixed yet, but the idea is something like that. And you flux. You have sweeper flux between, I don't know. You have to prove that your the mass transfer coefficient that is reached inside your hood is in this range. So this is an idea. What I also proposed was to maybe add an annex in the standard to, once you have verified the mass transfer coefficient of your hood, to indicate how to use it in case to relate it to the open field conditions. So how to use it for the estimation of other emission rates for dispersion modeling purposes. But this is something that was just an idea that I had in Ischia 3 weeks ago, and I think this will be one of the points that we will discuss in the next days during the meetings, together with this target approach idea that was discussed between the task group and the convener, I think.
Oh, I have one. Okay, if you pretend to regulate or to prove how the performance of your device, you have to set some parameters, right? And then if you think on a standardization, the regulatory body, the national regulatory body, may ask us, listen, you have to check every year that this is working, or so has to be an additional requirement for the guys, for the labs that are doing other measurements, right?
Probably. I'm not able to answer to that because honestly that it's still all in a proposal phase, so I don't know what will be decided. I think this idea of a target approach is a good compromise between not leaving things about area source sampling as they are now in the first version of the European norm, nor to give too strict rules which we are not able to give at the moment because the knowledge about it is still few steps behind. So this is something that will be discussed among us in the next days, and I think also the idea of rechecking or whatever could be something that we can decide together. I have no further information about that.
Okay, and I have another comment, and it's in Belgium for landfills. We have no Belgian guys here, but I'm told that in Belgium for landfills, it's so hard to rely on these measurements that they decided to just say, okay, we are going to do the plume measurement with the landfills. Might gives you maybe better estimates of the other emission of the landfill.
That's of course another idea, and probably it's a good possibility if you have very unhomogeneous surfaces in a landfill. So this could be another approach, of course. Honestly, when we decided to perform these studies, our first first goal was to prove that wind tunnels were not a suitable sampling method for landfills, because fact is that in 2005 we published a paper about other emission factors from landfills that has been cited a lot, and unfortunately the numbers we have given there are like 2 orders of magnitude higher than those we found now, and I'm really convinced at the moment that they were too high because we based our calculations on wind tunnel measurements at the outlet of which we had 70 or 80 other units per cubic meter, and you all know that's probably not very representative of the emission of odor from the landfill soil. So we started at saying, okay, let's try to get another sampling method, and that was the point behind this research activity. But of course, in a more general idea, it could be possible to think of other methods or of indirect methods as well. When you have such a complex source, it is, of course, a possibility. Even though also measuring such other concentration downwind in the plume is not, it's not easy. And we had also some experiences in doing the plume measurement with the field inspections, and it's very funny because you see this thing in the draft EN where you have to zigzag across the plume, and then you have rivers and agricultural fields, and that nice zigzag is not possible. So you have to find out a way to get to do something similar, but which isn't very. Is that flying across the plume, for example? And so finally, also indirect methods in some cases may entail quite a lot of problems.
Okay, thank you, Laura.